In this video, we are going to discuss the number system of digital electronics, in which we are going to discuss what is decimal and binary number system, and we will also see the conversion between decimal to binary and binary to decimal. Then we will discuss about some complement form, that is tens and nines complement of the decimal number system, and twos complement and ones complement format in the binary number system. Then we will discuss about the signed and unsigned numbers, and in the last we will discuss some previous year question from the GATE, ES and other examinations. So in number system, what is basically the base or radix? Base or radix denotes how many symbols in a given number system are there. For example, in decimal number system, we have total 10 different symbols that start from 0 and goes up to 9. So these total 10 symbols can form any number in a decimal number system. In a binary number system, we have two different symbols. So the base is 2 and these symbols are zeros and ones. That means any number can be represented by the combination of 0 and 1. Similarly, in octal number system, we have total 8 symbols that start from 0 and goes up to 7. In hexadecimal number system also we have 16 different symbols that start from 0 and goes up to 9, and we have some alphabets also. So in total we have 16 different symbols in hexadecimal number system also. What is base or radix? Base or radix denotes the different symbols in a given number system. That is denoted by small r. So the maximum value of the symbol can be given by r minus 1. For example, in decimal, we start from 0 and it goes up to r minus 1, that is 9. In binary, we start from 0 and it goes up to 2 minus 1, that is 1. In octal, we start from 0 and it goes up to r minus 1, that is 7 in this case. And let's discuss about the positional notations in a given number system. For example, in a decimal number system, we know the symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose there is a number given that is 7594, which has a base 10, that is it is a decimal number. So how we read this number? See, this number is 7594. Okay, so the base, or we can say the positional value at this position is 10 to the power 0. It has a positional weight of 10 to the power 1. This digit has a positional weight of 10 to the power 2. And this digit has a positional value of 10 to the power 3. And these digits are the coefficients. So we will find out the decimal number by multiplying the coefficient with the given weight. So this will become 7 into 10 to the power 3 plus 5 into 10 to the power 2 plus 9 into 10 to the power 1 plus 4 into 10 to the power 0. We know power of any number, that is m to the power 0, is 1. So this will become 4 into 1. This will become 9 into 10. This will become 5 into 100. And this will become 7 into 1000. So if we add these numbers, we will get 7000 plus 500 plus 90 plus 4. That will become 7594. That is our decimal number. Similarly, any fractional value can also be represented by its weight. For example, the given number is 2.75. 2.75. So we will start from this decimal point. So this 2 has a base, or we can say positional weight, of 10 to the power 0. And if we move after the decimal point, the power will be in the minus. So this will become 7. This will have the weight 10 to the power minus 1. Then it will have the weight of 10 to the power minus 2. So if we multiply the coefficient with the corresponding weight, it will become 2 into 10 to the power 0 plus 7 into 10 to the power minus 1 plus 5 into 10 to the power minus 2. And if we add all these numbers, we will get 2.75. So this is the basic concept behind the weight in a given number system. Let us now see how a binary number system is going to work. In a binary number system, we know we use two symbols, that is 0 and 1. these can represent two different states. So switches generally hold two states, that is on state and off state. On state can be represented by bit 1 and off state can be represented by 0. So switch when it is closed can be represented by 1, and when switch is open it can be represented by bit 0. And 1 and 0 also represent the closed switch and we can say open switch. And these 1 and 0 logic also represent true condition and false condition. So we can use the bit 0 and 1 to represent the different states. Suppose if we want these two bits to represent a large number of value, then we can group the bits. For example, we can take 2 bits and these 2 bits can have individually value as 0 or 1. So we have 4 combination in this case, that is 0 0 0 1 1 0 and 1 1. So by using two symbols, that is 0 and 1, now we can represent 4 different numbers. Similarly, we can have n number of bits to represent 2 to the power n different values. For example, 1 bit, if we have, it can represent 2 values, that is 0 and 1. If you have 2 bits, it can represent 4 values. If you have 3 bits, we can represent up to 8 values. Similarly, with the 4 bits, it can represent up to 16 values. Similarly, we can say to have total m values, how many bits are required, that is log base 2 m. Your base 2, it comes from the radix, that is radix is 2 in this case. For example, if we want total 32 values to be represented, then how many bits we require? We require log base 2 32. That can be written as log base 2 2 to the power 5, and we know log of m to the power n is n log base m. So this will be 5 log base 2 of 2, that is equals to 1. So we need only 5 bits. Similarly, for 64 values we need 6 bit, and if you want to represent values as large as 1024, then we need 10 bits.